Hi students, this is part 2 of the thermochemistry lecture. I think I'll be able to finish almost all of it in this video and then have a couple little addendum videos there at the end. But let's get started. So the last video left off going through this equation, which we can use to calculate the change in internal energy if we are given the amount of heat that's been exchanged and the amount of work that's been exchanged during the reaction or the process. And we talked about how this when you do this equation, that knowing the signs are very important, knowing whether the energy comes in or comes out, so whether it's positive or negative. So what I want to do now is kind of push forward a little bit and talk about the fact that in a lab setting or in science, these two measurements, or well, let me say these two parameters, heat and work, they are not things that you can directly measure. In other words, you can't go into a lab and say, I want to use an instrument to directly measure heat. Same with work, you cannot directly measure it. There's no like work-o-meter or heat-o-meter or anything like that. However, both of them you can calculate. So this is what we're going to give you here. Both Q and W must be calculated using metrics that you can measure. So we're going to actually learn an equation for both Q and for W. And these are very famous. So in order to calculate Q, Q is going to equal the mass of a substance times this new thing, which is called specific heat capacity, and we'll talk about that in a little bit and put some more stuff on it, but mass times specific heat capacity times delta T. Delta T being the change in temperature. So as you might imagine, when you heat something up, say you heat up a pot of water, the end result is that you are going to change its temperature. You can measure temperature. You can measure temperature changes. And if you can get the change in how much its temperature, in that case, goes up, and you can measure its mass, and specific heat capacity, what we're going to learn is something that can be measured, but for normal purposes, usually just look it up in a table, then you can actually calculate heat. You can get a number. So we'll do some practice problems with this equation. But before we kind of go into it too far, let me also give you the equation that is used to calculate work. Work can be calculated in a number of different ways, but the type of work that we are going to be thinking about in chemistry is called pressure volume work. And this is the work that gases do as they expand and they push against an external pressure. At the end of the day, I am not going to be asking you to do any calculations with this equation, but I do want you to have it memorized. In a little bit, we're going to refer back to it when I teach you about enthalpy. So work is equal to negative P delta V. Once again, though, these are things that you can measure. You can measure the pressure, you can measure changes in volume, and using things that you can measure, you can find out how much work is being done in a process. So these are two equations that you should have memorized. Now, let's go ahead and do, like I said, you're not going to be doing calculations with this one, just have it memorized. This one is definitely going to be used in calculations. Let me, even before we go into what this specific heat capacity is, let's just tell you right now it's a number that you'll be given, okay? So we'll talk about it conceptually in just a little bit, but let me go ahead and just right off the bat, just do some practice questions with this and so you can kind of see how this equation works. Let me go ahead and do two different practice questions. All right, we'll start with this one. Say you have a 90.0 gram iron block. And we're going to say it's heated from 35.5 degrees C to 47.9 degrees C. So you can see its temperature goes up. How much heat did it? Now, you can predict my next word. If the temperature went up of the iron block, did heat flow into it? In which case that's an input or a positive number, and you would use the word absorb. or did heat come out of it? Just think about it logically. If it got hotter, hopefully you recognize that heat must have come in. So the right word is absorb. Or at least that's the word that I was going to naturally write with this question. But I just want you to keep thinking about these signs as you're approaching these questions. All right. So at the end of the day, you will see if you have your textbook with you, and you will need a table of specific heat capacities. So let me see if I can find that page. In your textbook, it is on page 259. There's a table. Specific heat capacities are unique to each type of substance. So the specific heat capacity of iron, you would look it up. And like I said, I'm going to spend some time talking about what in the world that is in a little bit, but let's just use it first. Of iron is 0.449. And look at the units that come with it. That's always important to look at the units. Hopefully I've trained you in that. The units are joules over gram times degree C. All right. So now let's go ahead and start using the equations. We are trying to solve for heat. So we're going to be solving for Q. Q means heat. Mass. Now, that means mass. Hopefully you can see, based on the mass unit that is in specific heat capacity, what the unit would have to be. If mass is in kilograms, it won't cancel grams. So the mass must be in grams. Luckily, in this question, I gave it to you in grams, so we don't have to do any conversions. But be ready for a conversion. If it was in milligrams or in kilograms, you would have to convert it to grams in order to use this equation. So Q is equal to 90.0 grams. That was the mass of the iron block. Times the specific heat capacity, 0.449 joules over gram degree C. And you can see that the gram unit will cancel. And then delta T. Even in the same way, you can see our delta T is perfect, it being in Celsius. You don't need to put it in Kelvin. It's perfect in Celsius. Now, delta T. Anytime you have a delta, it's always the same, final minus initial. So all you have to do is figure out which one is the final temp and which one is the initial temp. So when you read it, it was heated from this to that, which means this is the initial temp, and that is the final temp. So go ahead and throw that in your calculator. Calculate a change in temperature, and note the sign. Is it a positive or a negative? 47.9 minus 35.5 is positive 12.4 degrees C. And that will cancel out that. And now it's just a matter of throwing it in your calculator. So I'll do the same. 90 times 0.449 times 12.4 is equal to 501.084, and when we look at the sig figs in the question, he had 3, that has 3, so let's go with 3. 501 joules is the surviving unit that never got canceled, and that is not ambiguous. A lot of people get freaked out by the sig figs. Only if you have a 0 at the end is that ambiguous. 501 joules is perfect. So that's the right answer. Now, notice, look at the sign on Q. It is a positive number. And it will be a positive number anytime your delta T is positive. If you think about it, these are always going to be positive numbers. So as long as delta T is positive, Q is positive. Doesn't that make sense? If the temperature goes up, if there's an increase in temperature, obviously heat came in. Remember, input is always an in, or is always a positive number. So that makes sense. Let's look at another question using the same equation, but actually asking a different thing. That was solving for Q. Let me give you a different equation that is just another way that these questions can sometimes be written here. Let's go with, let me make a point here. Let me put this in kilograms. A 0.869 kilogram piece of aluminum has a temperature of 94 degrees C. As it cools, okay, so we're just basically stating the fact that it was 94 degrees at the beginning. Now maybe you set it on a lab bench or something. It's going to cool because the temperature of the air is 25. room temperature. So it's going to get colder as it's sitting there, just using your common sense. You know things, the heat will leave into the surroundings, as we talked about before. All right, as it cools, it releases. And doesn't that make sense? Wouldn't it release heat as it's cooling? It releases, just picture if that's confusing to you, if it's hot and the room temperature is 25 degrees C and it's 94, heat will always flow from hotter things to colder things, and it will release heat. It releases 34 kilojoules of heat. Now the question, what is its final temperature? So hopefully you can see that in this equation, we're not being asked to solve for heat. In fact, we're given heat. We're being asked to solve for T final. So just let's keep that in mind. But I would say let's still stick with this equation and solve this out. So let's start by writing the equation. Q equals M times CS times delta T. You can just get rid of the dots if you like. Now, in my opinion, if you are solving for either T final or T initial, no matter which one you're solving for, I think it's easier to solve for delta T first. You'll see as you're doing the algebra, I think it kind of prevents a couple of mistakes. So let's just solve for delta T first. So if we want to solve for delta T, we need to get rid of M and CS on both sides. So divide both sides by M times specific heat capacity. So delta T is going to equal heat over mass times specific heat capacity. Okay, now what you would have to do is look up the specific heat capacity for aluminum. Every single type of substance will have a different specific heat capacity. Aluminum's is 0.903, write this over here, 0.903 joules over gram times degree C. You'll see that's a different number than it was for iron, okay? And so even in the specific heat capacity, you kind of can see logically, these are telling you the units that the other guys are going to have to be in, so they'll cancel. So when we go and put our heat in, our heat can't stay in kilojoules. It's going to have to go into joules, so that cancels out this one. So 34 kilojoules is 34,000 joules. Now, here's the thing about heat. You got to be real careful. Heat, you have to think about the sign. It either comes in or it comes out. This is really important. And so you have to use the appropriate sign. If it releases 34 kilojoules of heat, that's outputting heat. That's letting it come out. Releasing heat is letting it come out. And that means that that heat is a negative number. Negative 34,000 joules are what you put on top there. And then the mass was 0.869 kilograms, but once again, we need it in grams. So there's 1,000 grams per kilogram. So if you can even envision that conversion factor in your mind, you'll know that you're going to times this number by 1,000. 869 grams times the specific heat capacity, which is 0.903 joules per gram degree C. Now you can see that even within the denominator, the gram units are going to cancel. The joule units will also cancel. And what you'll have left is a degree C. And because it's in the denominator of a denominator, it bumps up to the top floor. So now when you put this in your calculator, okay, I would put in negative 34,000 divided by, but be careful. When you have like a multiplication happening down here in your denominator, you have to make sure that you enter that correctly in your calculator. I've seen a lot of people making this mistake. You have to put parentheses around that. Otherwise, you're not telling your calculator to do the right thing. So parentheses 869 times 0.903. And I am getting for delta T, I'm getting negative 43.3 degrees C. Okay, let me erase a little bit more so I can have some space here. That's the change in temperature. And now the last part of this is this. We actually wanted to know T final as our final answer. So delta T is T final minus T initial. And I put in for delta T what I just got, negative 43.3 degrees C. and I'm solving for T final. What will I put in for T initial? Its initial temperature, which was 94 degrees C. How can I get T final alone? You would add 94 degrees C to both sides. And I am getting 50.67 degrees C as a T final. Now, with this temperature, I didn't have any decimal places, so I think it would be best to report your T final with no decimal places, because this is like an addition subtraction problem with sig figs. So the answer would be 51 degrees C. And as you're doing that question, does that make sense? The piece of aluminum was 94, it cooled. The temperature should have gone down. And that's where you can confirm that it makes sense that it went down to 51. So that's really two different ways that you might be challenged with this equation, Q equals M CS delta T. So now, let's talk a little bit about that CS, that specific heat capacity. What in the world was that number? Obviously, you look it up in a table and you can use it and plug and chug and all that stuff, but what is specific heat capacity? Let's back up a little bit here. The way that I usually like to teach this is I do like to contrast the concept of heat capacity versus specific heat capacity. They're actually two different things. They're related, obviously, but they are different from each other. The first difference will be in the letters that we use to abbreviate. So specific heat capacity is the one that we've been using this whole time. That is capital C, little s. Okay? With capital C, little s, that means specific heat capacity, whereas heat capacity is just capital C. So that one doesn't have the specific part of it. All right, so let us start out like this. This is maybe how I'll start it out this time. Because with specific heat capacities, because you can look them up in a table, and hopefully you've already done that a couple times, and you see that like aluminum always has, what was it, 0.903 joules per gram degree C. It didn't tell you how much aluminum. It could have been a little nugget. It could have been a huge aluminum structure. As long as it's aluminum, it will have the same specific heat capacity. That is the classic definition of what we call an intensive property. We have talked about this concept before, but an intensive property depends only on the type of substance, not on how much you have. Only on the type of substance, not on how much you have. Like I said, it could be a tiny nugget. It could be a huge aluminum structure, a huge building made of aluminum. So that is what an intensive property means. Other intensive properties were density. So other ones were density. Remember, the density of water is 1 gram per mil, no matter if you have just a little bit of water or a huge amount of water. As long as it's pure water, it's always 1 gram per mil, the density. Another intensive property could be something like color. You know, this marker, if I have like, you know, this whole tip, or I cut off a little piece, it's still black, that kind of thing. It doesn't really matter how much you have. All right, so that's the first thing I want to say, is that specific heat capacity is intensive. Heat capacity is different. Heat capacity is an example of an extensive property. Which depends absolutely on how much you have of the substance. How much you have. Let me say a couple other examples of extensive properties before I go further with this. Mass. Mass is an extensive property. If you have a lot of water, it weighs more. If you have less water, it weighs less. Volume, same thing. If you have a lot of water, you have large volume. If you have a little bit of water, you have small volume. It depends on how much you have. How in the world is heat capacity in that same category? Let's kind of talk about just heat capacity just for a little bit. Okay, so the best way I can explain it with heat capacity is, well, let me explain it like this. We know that say you have a glass of, let's say it's a glass of soda, cold soda. Okay, cold soda, say you took it out of your fridge and you put it on your table. And remember, air temperature is about 25 degrees C. Hopefully most of you know that if you have a cold glass of soda and you put it on your table, it's going to get warmer with time. That's why people like to drink it fast. What's going on there with heat? Well, if you have a cold soda on your table, heat from the air is entering the soda. And your temperature is dropping. Okay, your heat from the air is going into the soda and the temperature of the soda is rising. It's getting warmer. That's why people don't like it as much. So what I want to show you is that as the soda experiences an increase in its amount of heat, okay, as the heat goes into the soda, as it experiences an increase in the amount of heat, you're going to have an increase in its temperature. You're going to have, that's what positive delta T is, an increase. Its temperature is going to go up. What we see here is something that we've used before. As heat increases, the change in temperature goes up. That is called a direct proportionality. We learned that with our gases. And what you'll remember is that you can write this statement, that heat is proportional to delta T. If one goes up and the other one goes up, that's directly proportional, and that's how we wrote it. For instance, when we did Charles' law, we did that volume was proportional to temperature. So Q is proportional to delta T. Now, if you remember, I'm just kind of reusing some old concepts here. If you remember, what we did with this is that when we got rid of the proportionality sign, we turned it into an equal sign. If you remember what we had to do there, we had to put in a constant right after the equal sign. And that would become Q equals C delta T. C is heat capacity. So what I would like to say here is that if you had to give a formal definition for what is heat capacity, it is the proportionality constant between heat and delta T. That's what it is. Between heat and delta T. It tells you basically their relationship. Okay, now sticking with this for just a little bit longer, just to make sure you understand it, you don't have to, record all of that. If you got this recorded, you could stick with me here for just a little bit longer. So if C is the proportionality constant between delta T and Q, let's think about the significance of that for a minute here. Say you have, because I think this does help, say you have 2 pots of water, one big one, like pasta, you're making pasta, and you have that on high on your stove, lots of heat coming in, and then you have another area on your stove where you have this tiny pot of water. And you also have that one on high. Okay, just think about this for a minute because it will help you understand heat capacity. If they're both on high, they're both going to be receiving the same amount of heat. If they're both on high, hopefully you can understand that. Okay, now let me start off with the fact, let me ask you this question. Which one of these is going to experience a bigger temperature change in a certain amount of time? So say you give it 1 minute. Which one of these, just using common sense, they're both water, is the temperature going to shoot up? Hopefully you'll recognize that this one's temperature is going to rise much quicker and faster than this one will. So with a certain amount of heat, say you give it, 50 kilojoules of heat or whatever, this one's going to experience a much greater temperature change. Okay, hopefully you can connect these dots with me here. If I give them the same amount of heat, let's just pretend that this number Q is 100. I'm just going to play with numbers for a minute so you can see how this works. If I give them the same amount of heat, talk to me about the size of their heat capacities. If this one, let's say that this one has a temperature rise of 20 degrees C with that amount of heat, and we just said this one will rise less. This one, say, will only rise maybe 2 degrees C. which one has a higher heat capacity? Just think about it. 100 equals C times 2, C would equal 50. 100 equals C times 20, C would equal 5. What I'm trying to show with numbers is that this pot of water will have a higher heat capacity. And how do we know? Because it resists the temperature change much better than this one does. The one with the bigger temperature change has a lower heat capacity. The one with a smaller temperature change has a bigger heat capacity. And so that's really what heat capacity is, and that's why it's an extensive property. It depends how much you have. If you have a lot of water, you're going to have higher heat capacity. If you have less water, you're going to have smaller heat capacity. And also, don't underestimate or don't underuse the word capacity. Capacity is how much heat something can hold successfully without freaking out and having its temperature rise. Higher capacity means, yes, it can take on that heat and it's not going to go crazy with the temperature. Whereas low heat capacity, its temperature rises quickly. So that's really what heat capacity is. Now that one takes kind of a long time to explain. Specific heat capacity will take less time. With heat capacity, obviously, since it's so subjective, it depends on how much you have. Scientists invented this thing called specific heat capacity. And so what they did is they said, all right, we know we need to kind of like normalize this so we can use these numbers here. So what is specific heat capacity by definition? It's the amount of heat required to raise the temperature of 1 gram of substance. So you notice here they fixate a certain mass, okay? So it's not all over the place like heat capacity, which can really be anything, of 1 gram of substance by 1 degrees Celsius. And that's what specific heat capacity is. They kind of choose how much we're going to measure. We're measuring 1 gram, and we're seeing how much heat you have to input to raise the temperature by 1 degree Celsius. Now, conceptually, it's going to be kind of similar, though. The higher your specific heat capacity, the more resistant the substance is to temperature changes. You know, when heat is absorbed. That's kind of how you can think about it. So when you look at those numbers on your specific heat capacity table, they still kind of relate. Look at something like water. Water's heat capacity is really high. It's 4.18 joules. That means that water can take in a lot of heat compared to something like a metal, which is lower, and not shoot its temperature way up. That's why, like, for instance, if the sun is shining on a swimming pool all day, it doesn't boil. It can take in all that sunlight and kind of, you know, get a little warmer, but not that warm. You don't have these wild swings. Actually, that's why in deserts where there are no water, there are wild swings between daytime and nighttime when the sun is there and when it's not. It's because you don't have water to kind of take in the heat and kind of keep it temperate. But anyhow, you can just think about it like that. The higher your heat capacity, the more resistant the substance is to like wild temperature changes. At the end of the day, this is a conceptual concept that I do want you to have a sense of, but this is the one that you are going to use in your equations. You will never, at least for my class, be using anything about heat capacity. But I did want you to understand it's a good example of extensive versus intensive properties. All right, moving on to kind of like the heart of thermochemistry, which is called enthalpy. That's like kind of like the main I don't know, the kind of like the most important part of, in my opinion, of thermochemistry as it applies to like chemical reactions. Okay, let's go ahead and introduce it like this. What I want to do is mention what are called thermochemical equations. And this will lead us into enthalpy. Okay, let me go ahead and write 2 thermochemical equations on the board. I wrote a couple down here. And then I'll talk about what they are. All right, so go ahead and write these with me here. So here's one. This is the combustion of methane, which we've done in class. So organic molecule reacting with O2 to make CO2 and water, vapor. Okay, that's a chemical equation. I turn it into a thermochemical equation when I write this thing to the right, delta H equals, and then I have a number here for you. I had to look this up, negative 890.4 kilojoules. And that is what we call a thermochemical equation. So a thermochemical equation, all that it is just a regular chemical equation. Reactants, arrow, products, just as usual, balanced and everything. Now, the one thing is, phase labels are essential with thermochemical equations. They're never optional. You always have to have them. Let me make that little note here. And what you have is this thing to the right called the delta H. Now, delta H, well, I'll talk about that one in a minute, but it's going to refer to change in enthalpy, okay? And it gives you a number. Okay, so we'll talk about what that is in a minute. Let me write one more on the board. Here's another example of a thermochemical equation. P4O10, solid. This is a decomposition, because you only have one reactant, and it decomposes into two products here. And this one has also, it's delta H, so that is what's going to make it a thermochemical equation, equals 3013 kilojoules. Okay, so I've got two chemical equations here, and I'll kind of use both to talk about what enthalpy is. So let's go ahead and ask the question, what in the world is that delta H? What is delta H? What is that? It's a very important part of chemistry, actually. So delta H is officially called the change, because it's a delta, in enthalpy. Enthalpy. So obviously enthalpy is what we use when we use capital H, okay? Now, sometimes I take longer with this than I do in other times. I think I'll kind of shorten this a little bit this time since we are, not meeting face to face. But what is enthalpy? Enthalpy is like a physics concept, and officially it is equal to the amount of internal energy in a substance, that's E, plus P times V, which represents the amount of work that a substance is doing on its surroundings to make room for itself. Real quickly, everything has a certain amount of enthalpy. This marker, I'll just use this marker, has a certain amount of enthalpy. The enthalpy will include all of its internal energy, which is all of its potential energy and kinetic energy going on in this substance. But it also adds in this concept that when the marker is moved from this hand to this hand, what it had to do was it had to push away all the gas molecules that were here, and it actually had to do some work on the surroundings to like nudge them out of the way and push them out of the way. So enthalpy includes both of those things, okay? Now, when I want to think about delta H, as long as I am at what's called constant pressure, see at constant pressure, and this is a very common thing to be at constant pressure, like anytime you're in a lab bench, you're always at constant like atmospheric pressure. At constant pressure, it's also true that delta H would equal delta E plus P delta V. This is kind of a famous equation here. All that I'm saying is putting deltas in front of everything because I'm trying to look at changes. But the one thing I didn't put a delta in front of was P, because P doesn't change. It's at constant. It's a constant number. So kind of just developing this equation here. Now, you'll remember that delta E is equal to Q plus W. So if I'm just doing like a little algebraic substitution right here, if I put in, instead of delta E, if I put in Q plus W, because I'm allowed to, if they equal each other algebraically, you're allowed to substitute. Delta E is Q plus W. And remember I told you earlier I wanted you to memorize this equation. Work is equal to negative P delta V. And I said I wasn't going to have you calculate, but I wanted you to know it. Here's why. If I rearrange this equation and put the negative on the other side, negative work is P delta V, by just dividing by -1 on both sides, I now have another substitution. P delta V is equal to negative W. So I can put in negative W right here. Now I've got really kind of what enthalpy really is. delta H is Q plus W minus W, so the W is gone in a nice way. And delta H is just the heat of a reaction as long as you're at constant pressure. And that's what that little P stands for. So a lot of algebraic stuff and physicsy stuff to get us to really how chemists think about delta H. When I think about delta H, like when I look at that or that, this is how I think about it, this is how you should think about it. Delta H is simply the amount of heat, because remember, it's Q. Delta H was equal to Q at constant pressure. It's just the heat part. That's all that delta H is, just the heat. It's simply the amount of heat that is either absorbed or released during a chemical reaction. And the only caveat is that this reaction is at constant pressure, which we will always just assume. So we're not going to have to worry about that part being addressed. So when I see that number is telling me how much heat is associated with this chemical reaction, because it's important. If I'm doing a chemical reaction, I'd like to know, is it going to get hot? Is it going to get cold? Is it going to burn down a building? Like, it's important. Chemical reactions have a lot of heat components. And by the way, yeah, I'll mention that in a minute. So that's really what delta H is. It's just telling you the heat part of the reaction. Now, looking at the signs is really important. If you have a delta H that is a negative number, like this one, this is what we call an exothermic reaction. If delta H is a negative number, that is an exothermic reaction. Exothermic means, a lot of people just learn like feels hot, feels cold. It's all fine, but I wouldn't go there first. When I see exothermic, what that means is heat flows out. Exo means out, like an exoskeleton exiting. Heat flows out of the reaction. And you can see that's consistent with everything that we've been talking about. And negative is an output of energy. Okay, that's what you will see for an exothermic reaction. If you have a positive delta H, like this one it's implied to be positive. This is what's called an endothermic reaction. And what that means, endo means in. Endothermic reaction means that heat flows into the reaction or is absorbed by the reaction. And that's how that reaction is allowed to occur, is that heat is going to have to come into the reaction. So the sign of delta H tells you quite a bit. This reaction, when it occurs, is going to produce heat. This reaction, when it occurs, is going to absorb heat from the surroundings. Actually, the surroundings are going to lose heat, and the heat will come in, rather than this one where the heat comes out. All right, staying on this a little bit longer, endothermic versus exothermic, because there is more to say. Quite a bit more to say, actually. Okay, for both of these reactions, you can draw what are called enthalpy diagrams, and these are actually very, very useful. And they are very, very similar to what we were doing in the last video with energy diagrams. The only difference is that you, instead of on the x-axis, instead of writing E, you're just going to write H. But it's going to be very similar. So these are called enthalpy diagrams. And they're used a lot in Chem 102, especially in Chem 102 with a bunch of different things that you can learn about. So let's kind of talk about the first reaction first. Let's look at our exothermic reaction. This is our exothermic one. And I know that based on the sign of delta H, the negative one, the negative number. We're going to write an enthalpy diagram for this reaction, which we remember is you still write reactants, arrow, products, but you write it kind of topographically, like up and down. Now, think about it with me here. If you have a negative number, and if a delta, let me write that here again. All deltas are always final minus initial, which for enthalpy is just products minus reactants. Like if it's a chemical reaction, you always just do products minus reactants, okay? If it's exothermic and you're getting a negative number here, what that means is that this number, the reactants, is larger than this number. That means the enthalpy of the reactants is actually bigger. So with an exothermic reaction, this one here, you would write the reactants up high. And then you would draw a down arrow and you would react the products down low. Just write it with me and then pause and make sure it makes sense to you here. That's what an exothermic reaction is going to look like. Oh, and by the way, reaction progress is what you would write on the x-axis here. That's what an exothermic reaction is going to look like on an enthalpy diagram. Once again, if it's exothermic, your delta H is going to be negative. That's the whole kind of hallmark of an exothermic reaction, which implies that products are smaller than reactants. 5 minus 10 gives you a negative number. And that's how you're going to get a negative delta. What does that mean? That means when this reaction occurs, these species, these types of substances, the methane and the oxygen, have an inherently higher enthalpy just within them. Remember, enthalpy is something that it has inherently, it's measured, just like I talked about my marker has enthalpy. They just have higher enthalpy in them than the products do. Now, when that happens, when you go from something that had a lot of enthalpy, which is kind of like energy, it's very related. It's a form of energy. If you had a lot of energy and now you don't anymore, what does that mean? That means all that extra energy had to come out. It had to show up somewhere because of the law of the conservation of energy. And it shows up in this form. When you have an exothermic reaction, heat is released into the surroundings. Heat flows into the surroundings. It comes out. It just spills out of the reaction. And if you have an exothermic reaction, this is where that feels hot, feels cold thing comes in. Say you have a beaker and it's exothermic, or a flask, and you're touching it with your hand. If heat is flowing out of that reaction, that is going to feel hot to the touch. Exothermic reactions feel hot to the touch because heat is flowing out from them into your hand. So what I want to make sure you have in your notes, in an exothermic reaction, you're going to have a negative delta H. What that implies is that the products have less enthalpy than the reactants, okay? And that's why you have a down arrow. That heat flows out into the surroundings during the exothermic reaction. Heat flows out from the reaction into the surroundings, and that it feels hot to the touch. Now let's reverse it. Let's talk about an endothermic reaction, like the second one that I have on the board. In an endothermic reaction, let me get my enthalpy diagram set up. Reaction progress on the x-axis, enthalpy on the y. Endothermic reactions will always have a positive delta H, okay? So a positive delta H will be a positive number. The only way to get a positive number by doing products minus reactants is that your products are higher than your reactants. That will get you a positive number mathematically. So this, with a endothermic reaction, your reactants are going to have to start out low, and your products are higher in enthalpy inherently. These just are higher energy species, and so the concept is just reversed. How in the world can you go from something that had lower energy in the form of enthalpy to higher energy? You are going to need to have supplied energy from the outside to make it happen. So with this one here, heat is going to, I'm kind of running out of room here. Let me make a little bit of space. With an endothermic reaction, heat has to flow in from the surroundings, or flows in to the system or to the reaction from the surroundings. And so this reaction is only going to happen if you're allowed to supply heat to it to take it from this place up the mountain to this place. And that's what an endothermic reaction, what that means. And let's talk about how it feels to the touch. If you have a reaction that's endothermic and your hand is on it, your hand is part of the surroundings. So you are supplying heat to the reaction. And that will give you the sensation, believe it or not, of cold. If you feel that, if your body is sensing that it's losing heat, it will feel cold to you. So endothermic reactions feel cold to the touch because you are the surroundings supplying the heat into the reaction to make it happen. All right, endothermic versus exothermic. Now, that's all conceptual. Oh, let us say a couple more things. I've been using chemical reactions for my explanations. However, chemistry is not always just about chemical reactions. For instance, when we have phase changes, this is just a little side nugget here. When we have phase changes, for instance, say you go from H2O solid to H2O liquid. This is not a chemical reaction because you're not actually breaking any chemical bonds. It's just a phase change or a physical change, but enthalpy is still part of this. This is still going to have a heat component. And I don't actually know what the number is by heart, and I don't really want to take the time looking at it. However, just think about it with me for a minute. If you go from a solid to a liquid, what are you doing? You are melting. Melting. During this process, this is melting. And, you know, just think about it for a minute. If you have a solid, you have species that are in these kind of fixed positions and they're vibrating, okay? But you want to move to a liquid where they can now slide past each other. Is that going to require an input of heat to happen and be endothermic? Or is that going to require an output of heat to happen and therefore be exothermic? Hopefully you can see that to get something that's barely moving to something moving a lot, you're going to have to add energy in the form of heat. So this is an endothermic process. Endothermic. Melting is endothermic. What I did there is just kind of logicked it out. You can just think about solids compared to liquids. Liquids have more energy, so you're going to have to supply energy to make it happen. However, to just help you out with a little bit, for phase changes, I think this is kind of a nice little diagram to have here. I've seen this help a lot of students on exams, even beyond my class probably. Solid, liquid, gas are the three phases, and you can go all different directions with phase changes. Let's just diagram this real quick. To go from a solid to a liquid, that's called melting. Scientists actually call it fusion, but that's okay, you can call it melting. To go from a liquid to a gas, this is called evaporating or vaporization. That's actually the exact same thing. I'm writing vaporization, but you could write evaporating. To go from a gas to a liquid, it's called condensing. To go from a liquid to a solid, that's called freezing in science. And believe it or not, you can actually pass over the liquid phase and go straight from solid to gas and from gas to solid. So that's two more phase changes. Solid to gas is called sublimation or subliming, but let me call it just sublimation. And this one, gas to a solid, the opposite, is called deposition. So what I've just diagrammed is all the possible phase changes that something can undergo, like water or really anything. And what we want to know is, just like you and I just talked about melting, anytime that you move anywhere on the right of this diagram, any rightward arrow are always endothermic. This can help you sometimes. And anytime you move to the left of the arrow, it's always exothermic. Because sometimes these are easier to think about than other times. Like melting is pretty obvious that you would need to supply heat. Obviously, an ice cube only melts once you put it on the table where it's warmer and the heat can come in. Freezing, condensing is a little harder to imagine sometimes. Certainly deposition, I think, would be hard. So this little diagram can help you understand which one of these are endothermic processes and which one of these are exothermic processes. It kind of simplifies it a little bit. Okay, now let's kind of talk more about these thermochemical equations. And what can we do with this information? Let me erase my second one, and I'll just stay on this first one for a minute. So when you are given a thermochemical equation, you actually have a ton of information there. When I see delta H and I see the number, I almost verbalize this, you know, in my head. Here's my little thought bubble here. What does that number mean to me? Okay, and this is what it should mean to you too. The sign is just telling you whether the heat comes in or comes out. So in this case, this one is releasing heat or producing heat or evolving heat. This is telling you how much heat. So what I would say when I see this is I would say there are 890.4 kilojoules of heat released. Okay, it's released because it's negative, it's exothermic. When? When what? When am I going to get that much heat? Here's the issue with thermochemical equations. As soon as you put a delta H there, your coefficients now represent the number of moles that are reacting. Moles, not molecules, moles. So there are 890.4 kilojoules of heat released when 1 mole of CH4 reacts with 2 moles of O2. And I'm running out of room in my thought bubble, but you could also say producing 1 mole of CO2 and 2 moles of H2O. So what that's doing is it's telling you, hey, this is how much heat to expect when you do this reaction with that much stuff. If you have less moles, you would get less heat. Just think about if I burn, you know, a little tiny fire, I'm not going to get as much heat than if I have a huge bonfire. It's the amount of heat that you're going to get. It's expensive. It depends on how much you have. How do I use this information in math or problem solving? Let me show you how this shows up here. Practice question. If I have methane and I'm burning it, can you calculate the amount of heat released when, okay, real world, when, let's go when 38.0 grams of methane is burned or combusted according to the above reaction. Okay, so now I've got one number in my question, 38.0 grams. This is a dimensional analysis question. You can just conquer this just with conversion factors. I've got 38.0 grams of methane. If I don't know what to do, when in doubt, mole it out. Okay, so this is not a Q equals MCS delta T. Notice I have nothing about temperature changes here. Okay, there's nothing about temperature changes. This is asking you for the amount of heat when this mass of reactant is burned. So let's mole it out. CH4 is 16. I'm trying to do it in my head, but I'm scared. So let me, 12.01 plus 4 times 1.008. Yeah, 16.042 grams per mole of CH4. And here's where we have a new technique here. When you are given the delta H, you can relate the delta H, the amount of heat, almost like stoichiometry. Just like you can relate any of these to each other through mole-to-mole ratios, you can kind of bring him into the mix. And you can say, I'm going to get for every 1 mole of CH4, because that was a 1, I am going to get 890.4 kilojoules of heat released. Now, some people, you'll notice I dropped the negative sign. The negative sign is just telling you that it's released, and it's almost implied in the question. If you look at the question, it says they're trying to ask for the amount of heat. It's already implied that it's going to be released. So this is like an absolute value type of concept here. This is how much heat you're going to get coming out. So I usually just drop the negative sign in this type of question. So 38 divided by 16.042 times 890.4, and that is 2109 kilojoules. And let me think about sig figs. This one only has 3 sig figs, so I can only report 3. And with this kind of big number, I would need scientific notation. So 2.11 times 10 to the third kilojoules would be the amount of heat that a person could expect would come out of this reaction if they burned it, which is very important to know. You have a container, it's going to have to be able to absorb that much heat. There's safety issues, you need to know that how much energy is going to come out of that thing. So that's what deltaH, that's why this is a huge piece of information in terms of chemistry. It's really kind of telling you, hey, expect this much heat to come out of it. Let's go ahead and just do one more. Let's see here. Let me do another a different thermochemical equation. Let me pick one that has, how about this one here? Let's say you've got this chemical equation here. 4NH3 gas, so that's 4 moles of ammonia, reacting with 5 moles of oxygen gas to produce 4 NO gas plus 6 H2O gas, and this would all have to be given. And this thermochemical equation is negative 906 kilojoules. So what this is telling me is that obviously it's exothermic, okay? So 906 kilojoules will be released every time 4 moles of ammonia reacts with 5 moles of O2 to yield 4 moles of NO and 6 moles of H2O. So let's try another practice question here. How about maybe coming at it from a different point of view? Let me see if I can grab, how about this one? How many grams, this is going to be from the opposite point of view. How many grams of ammonia would be required to produce I'm trying to see if I can get a number that kind of makes sense. How about to produce 1,045 kilojoules of heat, according to this equation, okay? So you'd have the equation associated with it. So this time, I'm actually given the amount of heat. Maybe I'm trying to generate heat. Maybe I'm trying to do something that, I want to warm something up. This is the amount of heat I have, and I'm asking for how many grams would be required according to this reaction to get that much heat. Once again, dimensional analysis. Just start with the one question, the one number in the question. So I've got this many kilojoules of heat, 1045. Now, with this one here, you can see in the wording, it's going to produce this much heat. So there's a couple different ways to do it. If you want to put a negative here, just understanding that that heat is coming out, it's being produced, that's fine. So let's just do that for now, and I'll show you what I mean by that. So now I need to figure out a way to turn kilojoules of heat into grams. Understanding that when you have a thermochemical equation, you have a conversion factor. You have relating this amount of heat to whatever one the question is about. In this case, ammonia. I'm going to relate it to this. So you just relate it to whatever one the question is about. So write a conversion factor, and the conversion factor would say, I'm going to get 906 kilojoules of heat released when. Now, if you put the negative here, you're going to have to keep the negative here. It's like a choice. Just be consistent. Either keep them both or drop them both. At the end of the day, you're going to get a positive number for mass, which is the only possibility. So I'll just keep them both. Negative 906 kilojoules of heat released when. Here's the thing. You've got to include that 4. You're only going to get that amount of heat when you have 4 moles of ammonia reacting. That's the only possibility. That's the amount of heat when 4 moles react. And remember, the coefficients represent the number of moles. And now you can see kilojoules will cancel. So you're just building a conversion factor. And hopefully everybody knows by now to go from moles to grams is just molar mass. And the molar mass for ammonium is 17.034 grams per mole. And now just go ahead and throw that into your calculator. And you can see that the answer will make sense. Negative 1045 divided by negative 906 times 17.034. You would need 19 point, now sig figs, this one has 4, this one has 3, so I'm going to be limited by 3. 19.6 grams of ammonia is how much you would have to react with oxygen to get this amount of heat. So you can really ask these types of questions from both points of view. All right, now, the last thing here, how are we doing on time? We're at about an hour. Let me go a little longer and do Hess's law, and then we are really kind of did everything that we need to do for today. And we're really actually almost done with the thermochemistry unit. Okay, so let's see. Let me write a couple. Let me call this relationships involving delta H. Okay. Let me pick a very simple reaction to illustrate this. Yeah, let's do this reaction here. Say you have this reaction, 2H2 gas plus O2 gas yields 2H2O gas. And I have a delta H. So I have this thermochemical equation, and this is negative 486.6 kilojoules. Once again, another exothermic reaction. Let me make sure I have this. So say I give you this. I just want to make sure it's right. Okay. We have a thermochemical equation. What things can we do with it? Okay, so the first thing I want you to know is that if you reverse the reaction, and we talked about reverse reactions last time. If you reverse a reaction, that essentially just means you write it backwards. Whoever was the product now becomes the reactant, and whoever was the reactants now become the products. So I just reverse the reaction. If you reverse a reaction, you basically flip the sign of delta H. So if you knew the reaction, or sorry, if you knew the delta H of the reaction when it was forward, you actually know the delta H of it in the reverse. And it's literally going to be the opposite, the same number, opposite sign. So if this was negative, then this one becomes a positive 486.6 kilojoules. So that's the first thing. Anytime you reverse a reaction, just flip the sign of the delta H. Now, what does that mean? That means for any reaction that's exothermic, its reverse is going to be endothermic. And frankly, that makes a ton of sense, because if you had a reaction that was exothermic, you'll notice it was that's just reactant arrow products. When you go downhill and be exothermic, if you're reversing the reaction, you're going to be endothermic. It really actually makes perfect sense. So the reverse of an exothermic reaction will just be the same number, just endothermic, or just the positive number. So that's the first thing I wanted to say. The second thing I wanted to say is, if you multiply a reaction by a factor, say, for instance, if you multiply it by 2, what you do is you multiply the delta H by the same factor. Okay, so starting with this reaction here, let's take our eyes right here. It's my eyes. Okay, if you have this reaction, say I want to multiply, and you'll maybe see with Hess's law why we do this. Say I want to multiply this by some factor. It can be times 2. It can be times 1/2. It can be times anything that you want it to be. But let me multiply it by 2. Not only will you multiply the coefficients and all of them, you have to, if you do something, you have to do it to all of them to make sure it stays balanced. You will also multiply the delta H by that exact same factor. So say you have this reaction, which would really double the amounts, like 4H2 gas plus 2O2 gas. I'm just multiplying them all by 2. And maybe you don't understand why I would do this. You'll see why with Hess's law. But for now, just accept it. You can, as long as you knew the delta H of the original, if you multiplied everybody by 2, you also have to multiply him by 2. And once again, that really also makes sense. You're going to get twice as much heat if you have twice as much stuff. So 2 times negative 486.6 would be negative 973.2 kilojoules. So those are 2 things about delta H that you should know. If you reverse it, flip the sign. If you multiply the coefficients by something, you have to multiply the delta H by the very same thing, very same factor. If that had been a half, you would multiply all of them by 1/2, including him, which is the same thing as multiplying it by 0.5 or dividing by 2, actually. All right, last thing about thermochemical equations is they are subject to this thing called Hess's law. And what I'm going to do is put up a worksheet. I actually printed one out. Hopefully I can find it. Yeah. Of practice questions. You definitely are going to need to learn how to do Hess's law questions. It's a 2-page worksheet. I will do, I'll do number 2 with you here on the board. It's 1 through 4, okay? And I will put on the Blackboard announcement the answers so that you can know what the right answers are. But I'm going to do number 2 with you. I think that would maybe be the best one to teach this. So what in the world is Hess's law? This is like, you know, the third thing I want you to know about this. Hess's law. Hess's law basically just states if you add 2 equations together, 2 chemical equations together, you just add their delta H's together as well. Okay, that is not the prettiest definition. I literally made that up on the fly because I know that the longer definition would have taken like 3 times as long to write on the board. But essentially, Hess's law, you'll just kind of do it with me and you'll see how to do it. But basically, we're going to be adding up equations together to figure out an overall equation, and then you're going to see you just add up their enthalpies. Let me explain it with an example. It's just so many of these things are just better taught with an example. Okay, here's how this works. I'm actually doing number 2 with you, and it says, use the thermochemical equations shown below to determine the enthalpy for a reaction. So let me put this one up on the board. Oftentimes, a scientist is going to be doing a chemical reaction, like say they're trying to do this one, and maybe they cannot find the delta H. Maybe it's not known yet, okay? And before they actually do the chemical reaction, they're like, hey, I better find out how much heat I'm going to get released from this reaction. And, you know, it's an important thing to know. Or does the reaction absorb heat? Do I have to supply heat to it to make it happen and all of that? So this Hess's law concept is a way to figure out delta H on paper rather than having to just do the reaction and kind of figure out the amount of heat using calorimetry or some other method. All right, so the goal of Hess's law is to figure out the delta H, or the change in enthalpy from a reaction. With Hess's law problems, you will be given some steps. So these steps are provided as part of the reaction. So this one, or as part of the problem. So 1/2 N2 gas plus 1/2 O2 gas yields NO gas. And with the steps, the delta H's are known. So this is 90.3 kilojoules. Okay, so a scientist, maybe he goes into, or she goes into a textbook and finds some steps, you know, with known delta H's. And here's the second step. NO gas plus 1/2 Cl2 gas going to NOCl gas, and this one has a delta H equal to negative 38.6 kilojoules. Okay, so this is the setup of the problem. This would be given on the exam or whatever. And the way that this works, it's almost like a little puzzle. Let me get a different color marker. It's helpful to have two different pens with this thing here. What I want to do is I want to get these two steps to the point that when I add them together, so let me kind of set this up. This is a good way to do this. When I add these two steps up together, they look like this. So this here is like your goal. This is the one that you're trying to get written down here so that it's the result of adding these two up. All right, so what you do as a problem-solving technique is you stand back for a minute, and I just always start with the first step. And I come over here and I say, all right, you ask two questions. Okay, the first question is this: do I need to reverse this reaction in order to get things on the correct side? So go ahead and just take a look at, the first thing that you see. I see N2 right here. Right now it's a reactant. When you look up here, you can see that it's actually a product. And this step is the only step for which N2 is present. It's not even present down here. So I have to end up getting it on the correct side here. Like, this is my only shot to get it correct. So I just make myself a little mental note. I'm going to need to reverse this reaction in order to get it on the correct side. This is my goal. Okay, it needs to be a product. Right now it's a reactant. But before I proceed any farther, I also want to ask my second question. So first question is, do I need to reverse it? Second question is, do I need to times it by something so that the coefficients are correct? Right now, the N2 has a coefficient of 1/2. I need the coefficient to become a 1. And so therefore, I am going to not only have to reverse it, but I'm going to have to multiply it by 2. And you want to do both of these at the same step. Don't be tempted to do one thing at a time. It will make you insane. So I'm going to both reverse this equation, and multiply all the coefficients by 2. So reversing it just means taking that product and making him the reactant. But notice the 1 is going to have to become a 2 because I'm doing both of these treatments. It's kind of like you're manipulating it a little bit. You're messing with it a little bit. So I'm not only reversing it, but I'm multiplying everything by 2. And now I draw the arrow. Now I write my reactants as the products. 1/2 times 2 becomes a 1. And same here. And keep your phase labels. 1/2 times 2 becomes a 1. Okay. Now I've just basically done those 2 manipulations to my step. Now understand, based on what we just talked about before, if you reverse an equation, you flip the sign. So what used to be positive is now going to have to be negative because I've reversed it. But not only did I reverse it, I also times everything by 2. If you times everything by 2, you also have to times the delta H by 2. So this becomes negative 180.6 kilojoules for this new form of the equation. I just basically executed the rules about delta H. Flip the sign and times it by 2 because I times everything by 2. Okay, now once you've done what you can with your first step, go on to your second step and ask the same 2 questions. Do I need to reverse it? Well, NO doesn't even appear in the overall, so don't make any judgments if you can't even find it appearing in the overall. It's going to disappear when we add them together, but just move on to somebody else that you can see. Cl2. Cl2 is a reactant here. I need it to become a product. So clearly I have to reverse it. Not only that, you can see NOCl is a product. I need it to become a reactant. So I have to reverse this equation. And the second question before I move on is, do I need to multiply the coefficients by something to get them correct? I'll just use NOCl. NOCl, it's a 1. I need to make it a 2. So in the same way, I'm also going to have to not only reverse, but also multiply this one by 2. So now go ahead and do it. Reverse and multiply by 2. 2 NOCl gas becomes 2 NOs plus, that will become a 1, Cl2 gas. And delta H is the opposite sign flipped. So now it used to be negative, now it's going to be positive. And 38.6, I'm going to have to times it by 2. 77.2 kilojoules. All right, that is the delta H of this new manipulation. Now, the final step to Hess's law. Now I'm going to add these two equations together. And Hess's law basically states that if you can add two equations together and make it match your goal, then the delta H of your goal is just going to be the addition of these two. So now let me show you what it means to add two equations together. Adding two equations is actually pretty simple. All that means is that you, here's my arrow, is that you kind of collect all the reactants from both of them. So 2NO gas was a reactant from him, and 2NOCl gas is a reactant from him. So just adding the equations is just collecting all the reactants. And now go ahead and collect all the products. In any order. Remember, chemistry doesn't care which order you put them in, as long as they're all products. And I'm just writing all the products from these. And now you can usually do some canceling. Hopefully you see that I've got 2NO gas on the left, and I've also got 2NO gas on the right. So these, as long as it's the same number, you literally can cancel it or subtract it from both sides and they go away. So those are actually gone, and you can see that my goal has actually been, I basically got them to the point where you add them together to get your goal. So see how it matches. 2NOCl gas yields N2 plus O2 plus Cl2. It's the same thing as what's above. Hess's law states that now that you have that, you can know his delta H by just taking the addition of, see, if I added these two in blue, that's why I'm saying it helps to have two different colors. If you added these two equations, then all you do is add their delta H's. So the very last step is just add the delta H's of those two that you manipulated. So it's going to be 77.2 plus a negative 180.6, and I'm getting negative 103.4 kilojoules as an answer. And that is the right answer. I've just discovered how much heat is going to get released from this. I didn't have to do any experiments. I just used some kind of known equations. And you can imagine that scientists have collected all this information over the years. They have all these steps and books, and you can just kind of piece them together and figure it out. So what I'm going to do is have 3 more chances for you to kind of conquer this. And then maybe when we do an exam 3 review, I'll do one of them or whatever. There's more in your textbook. You can always Google Hess's law, practice problems, videos, or whatever. Everybody will likely do it the exact same way. The point is just stay organized. Always ask the same 2 questions of your steps, and then just kind of, change delta H accordingly and add them up together. It does take a little bit of practice, but once you get the hang of it, it's actually one of the more fun things. It's like a little puzzle in chemistry, and once you get the hang of it, it actually can be kind of fun. So download those Hess's law problems that I will put up there, and see if you can conquer them. And I will put the answers there so that you can have confidence that you're doing it right. That is a good place for us to stop with this video. Thank you for your attention, and good luck with thermochemistry.